Hello and welcome. Today we're going to be examining a hypothesis test that you'll be able to use, the independent samples t-test. This hypothesis is designed to look at the relationship between two means. So in order to do this, what we need are two variables. The first variable needs to be a metric level variable, and by metric I mean something that's ratio or interval level, so we can calculate a simple mean on it. The other variable we need is a dichotomous variable, so a nominal level variable that only has two categories to it. So it's simply a label. Today we're going to be doing two samples. One is going to be examining gender and how the months sentenced to prison vary, and the other one we're going to be doing is looking at race, coded in a dichotomous way. Once again, looking at the months in prison the individual defendant received. But once again, we're going to be using SPSS version 23, that's statistical package for the social sciences. Using version 23, once again, most versions backwards are going to have the same types of commands, so you should be able to use this information even if you're using an older version. So first things first, we want to talk about the variables that we're going to be using. So once again, for this video, we're going to be using three major variables. One is race dicot, which is simply race in a dichotomous coding. So we have white defendants and non-white defendants. We will also be using gender, which is coded as monsex, and this will be coded as males and females. And our metric level variable is going to be number of months the individual served in prison. So first and foremost, we always want to run a quick descriptive analysis on these variables. So we'll go ahead and take a very brief look at these. We'll pull monsex, or we'll pull dichotomous race, and we also grab months in prison. Now I'm not going to get the frequency tables, but we will grab some very basic statistics. We can get a mean calculated for each one, just to know what that is looking like, and calculate. So here we know within these two variables how many cases there are: 68,000, 71,000, 72,000. How many variables are missing, and then the calculated mean for each. So what this means is that defendant white, non-white, because we're calculating between a 0 and 1, and white defendants being 0 and non-white defendants being 1. So this average tells us that 71% of our sample are non-white defendants. Same thing for gender. We examine seeing males are 0 and females are 1. That means the average for this is 13%, so 13% of our distribution essentially are female, and then the average number of months in prison is 49.93. So what we're going to do is we're going to examine defendants' gender and the race variable in a dichotomous coding. And we're going to basically examine the two categories for each one of those variables and see the mean for each of the subgroups for that variable, if they're different or not, essentially, based on the sample size. Once again, we're playing with a sample size that is so large that likely anything in here is going to be statistically significant. However, walking through the steps, we'll be able to kind of demonstrate how you would do this. So first off, let's start with gender, and let's start with that. So we're examining basically the average sentence length for men and the average sentence length for women, and we're going to examine if there is a statistical difference between the two. So is this difference supposed to be found in the general population? Is this something that would that is a true difference, or is this something that's so close that we really can't say there's a true difference here? So the first thing we're going to do in order to run this test is we're going to go to Analyze. Okay, go down to compare means, because that's essentially what we're doing. We're comparing the means for these two groupings within this variable. And we're going to go over to independent samples t-test. And the independent sample is because the two means that we're going to be comparing are not attached to one another, essentially. We didn't do a pre-test or a post-test or something of that nature, so the two samples are independent of one another. So we're going to grab that, and we're going to pull over our test variable, which is going to be months in prison. So your test variable is your metric level variable. This is the variable measured as ratio or interval. So pull that over into the test variable. And for the grouping variable, we're going to go ahead and grab monsex, because that is our dichotomously coded variable. When you pull this over, you're going to get two little question marks in a parentheses, kind of indicating that it wants additional data, and what it wants you to do is define the groups. So if there were more groupings, so for example, we had 0 being male, 1 being female, and 2 being a transsex or something of that nature, then what we could do is we could only define between 2 of those 3 groups. So we want to go in here to define groups, and it's going to ask us group 1, group 2, which ones do we want to compare. So males were 0 and females were 1, so we can enter those values in and click OK. And at this point, the groupings are defined, and we have our testing variable or metric level variable. Let's run this. So when we click OK, we're going to get our output. Try and expand this screen so we can easily take a look at it. So this first box is going to tell us the information about the 2 groups. So for males, there were 61,000 within the sample, and the average sentence that men received was 55 months approximately, the standard deviation of 79. With females, there were about 9,400 and a few more. Their average sentence was 23.6. So the question becomes, is this difference, right, between 55 and 23 months statistically significant or not? So in order to answer this question, we're going to go down to the independent samples t-test, and we're going to examine this box. Now, down here, one of the first things you want to look at is this Levene's test for equality of variances. And essentially what this is doing is it's testing to see if there is, a significant variation in the variance between them, essentially the spread of the data, once again. And we want to be testing similar variance against one another. If this comes back, the null hypothesis here basically is testing to see if the variances are equal. If the variances are not equal, it'll actually come back as statistically significant. So essentially, here's the rule. If the sig category right here is 0.05 or below, so 0.05 all the way to 0, this means your variance is not equal, and we will use this grouping down here. However, so variance is not equal. If this would have been over a 0.05 or over that point, all the way to a value of 1, we could assume that the variances are equal. And all this does, it just looks at to which of these columns we're going to interpret. For many situations, it's not going to matter all that much. Both might come back statistically significant or might not. However, to be precise, you do want to make sure you select that. So in this case, we are statistically significant, which means we do not have equal variances. So we will use the bottom grouping, okay, the bottom row here. So our t-value, our comparison between the 2 groups is 59, and this is statistically significant. Now, once again, to test or to examine for statistical significance, typically we're going to be using the 0.05 significance level. Sometimes in larger data sets, you might want to use a higher level of statistical significance. But if we're just using the simple 0.05 level, then we can see this is statistically significant, and this makes sense once again, right? The mean difference, or the difference between the 2 groups, is 31 months, which is a large number. So it makes absolute sense that there's a very large difference between these 2 groups. There are a lot of cases which additionally feed into the statistical significance. It makes absolute sense that this would come back statistically significant. So in this case, we can say absolutely that there is a difference between men and women, and it is statistically significant. So we could generalize this finding back to the entire population, in this case of all prisoners in the federal sentencing, or that were sentenced for in the federal system. So let's do one more example here real quick so we feel comfortable with this. Let's examine race at this point. Once again, I've done a very crude coding of race between white defendants and non-white defendants. So that's basically, we're only dealing with these 2 groups. Once again, probably not ideal coding. It's done sometimes in the social science, but if you can find the individual groups, it would be ideal. So once again, we're going to go to Analyze, drop down to Compare Means, slide over to Independent Samples t-test. Go ahead and reset this. However, months in prison would still be our metric variable. So what we're going to be doing is we're going to be comparing the number of months in prison for white defendants and non-white defendants and seeing if that difference between the 2, or if there is a difference, is statistically significant. So we're going to pull the race dichotomy over. Once again, the dichotomous race variable is 0 for white defendants and 1 for non-white defendants. So we can code that 0 and 1 and bring that in. So once again, our metric level is defined, metric variable is defined, our grouping variable or dichotomous variable is defined, we can go for it. So if we click OK, once again we get the output screen that gives us some really critical information. So in this situation we see white defendants in this sample of the federal sentencing dataset received 48.8 months in prison on average, where non-white defendants received 53.5 months. So this is a difference of about 4.5 months. Now it's a much shorter gap, or a smaller gap, than we saw in the previous model between men and women. So once again, the question becomes, is there a statistically significant difference between these two? Can we take the difference that we found here and generalize it back to the population? So we go down here and once again look at a Wien's test for equality of variances, because this is going to tell us whether we assume equal variances or we cannot assume equal variances. In this case, the test is over 0.05, so we are not significant. And remember, the null is that there is no difference. So because this is over 0.05, we actually use the top row this time. And we can come down here and find our t value is negative 7.3, and all the negative means is that it's subtracting, taking 48 minus 53. If we had flipped these codes, we'd entered grouping variable 1 and 0 instead of 0 or 1, these negatives would then become positive. So don't freak out, don't worry about if it's a negative or a positive. So once again, this number is only being calculated from the top minus the bottom. So our t value is 7.3, and this is statistically significant, less than the 0.05 value we typically use for statistical significance. So this means even a difference of 4.69 months between the two is statistically significant. We can generalize this finding back to the entire population. Once again, that's really being driven by the large number of cases that we have in this sample. So if you have any questions, don't hesitate to contact me. Hopefully this has helped clarify and given you some just basic commands to be able to run an independent samples t-test. And once again, you would use this tool whenever you want to examine a mean or an average between two different groups.